Okay, so now we'll talk about potential bottlenecks to automating research or to getting explosive growth really quickly or perhaps ever as a result of automating research. So first, there's this point that R&D might just not be that computerizable after all. So Ege Erdel and Matthew Barnett have a recent article arguing that R&D is not particularly susceptible to automation, despite the um, arguments we've thrown out earlier. And this is because many research workflows hinge on things that computers can't do, or at least seem a long way from being able to do, such as performing physical experiments, complex coordination, and long horizon planning. And this is even true to some extent of AI R&D. So RLHF, for instance, obviously requires human feedback. Um, that's what it is. So you can't delegate it to a computer. They do this interesting exercise of having GPT 4.5 label ONET tasks across R&D occupations into those that only require abstract reasoning, those requiring complex computer use skills, and those requiring a physical presence. And they find that for that across occupations, 5 to 60% of the tasks require physical presence, and 10 to 50% of them require complex computer use, as you can see in this graph here, right? So, yeah, for physicists, maybe only 5% of the tasks require a physical presence or something. Maybe this looks like 10. Yeah, okay. So for epidemiologists, only 5% of the tasks require a physical presence, but um, um, but you know, complex computer use of a kind that maybe seems hard to delegate to some kind of super LLM. That's still a kind of non-negligible proportion. And what this suggests is that by the time we can fully automate R&D, we'll also be able to automate lots of production. So focusing on these cases like we were talking about this morning, in which first we automate R&D and then we get explosive growth following, that might just not really be realistic. Another kind of constraint is, a lot of these stories on which we're on track almost inevitably to create AGI and see everything that follows from it, are kind of centered around a compute-centric framework in which we just crank out more and more compute, and somehow, models trained with enough compute get really intelligent. But the standard scaling laws of governing at least, pre-training for these models, in particular the chinchilla scaling laws from Hoffman et al. In 2022, tell us, and I think common sense might also sort of tell us, that increasing compute alone has bounded performance gains. You also need the data to be scaling alongside the compute, and that's kind of what the compute's doing, is it's being it's making use of all the extra data. So this is what the formula looks like. We'll see more about it later, but basically loss is average next token prediction error on test data, and that equals some irreducible loss plus these two terms, which can fall to zero as the inputs grow to infinity. And the inputs are data and parameters, or model size. And compute is basically, it's proportional to the product of the two things. So you could rewrite this as saying the two inputs are data and compute per data point, right? N will be R over D. R is the research input here. So I'm letting training compute be noted R. Anyway, what this means is that to keep improving AI performance on R&D tasks, we'll need more and more data, arguably, on how R&D is done. And that data might not always be the kind of thing that AI can collect or generate. In some contexts, it might just be very expensive to. So for example, how much data do we have on all the nitty gritty of how to run a chemistry experiment? I don't know. I don't know. I'm not a chemist, but it seems possible that some some of the rarefied details of how to perform some experiments are not, they don't have WikiHow videos online or anything. We might think that we're in a sort of learning by doing model. So this is sort of the point made on a grander scale, where the data needed to improve our performance on kind of doing the full range of valuable R&D tasks, even not even just tasks in production, but even just for R&D, maybe you need like accumulating data from the economy as a whole. In which case, the economy-wide lambda over beta, the like economy-wide rate at which we're getting faster at doing things that generate the data that we need as we scale up research inputs is going to be what matters for that feedback loop, not the hardware and software specific lambda over beta, because you can send like the quantity of hardware and the quality of software to the moon, but that won't be generating one of the necessary input. You'll be piling up a lot of compute, but we won't be piling up a lot of data, which you need to actually kind of increase performance, increase intelligence. Even for AI R&D, which seems an especially kind of computerizable kind of R&D, it's not clear that we have sufficient data on like the details of how AI researchers operate. We don't have, a million hours of screen recordings of AI researchers. Though I'm sure, people are gathering it. That kind of thing. Okay. So those are all kind of ways in which it might be hard to automate R&D, at least using kind of standard, AI on a computer. Then there's the question of the extent to which automating R&D would actually deliver really rapid productivity growth. And one kind of crux here is the extent to which productivity growth is in fact driven by R&D. So the Jones model is designed to explain the fact that growth in technology, basically just measured as output per person, more or less, maybe after controlling for fluctuations in capital. But anyway, growth in technology has been roughly constant, while population has also grown constantly. And Jones's explanation of this is that, tech grows due to R&D, and we've been having this ever-growing like population of researchers, but ideas are getting harder to find, and that's offsetting that. But an alternative explanation, just kind of for illustration, would be that output per person has largely grown for reasons other than R&D. So maybe increases in specialization or decreases in misallocation. We'll talk a bit about both of those. And that we've been running out of these sources of increases in output per person. And if that's right, automating R&D, well, that's just a small slice of the pie. So we could grow that quickly, but that'll do less to turn the tide of constant or even slowing productivity growth or technology growth. So as an extreme case of what I'm getting at here, suppose that we've been wrong all along and the only thing driving growth in output per person is specialization. Okay, so we've got these increasing returns to scale due to specialization. There's no A or anything. There's no B in the picture. Here, automating R&D won't speed growth at all. Now, automating production probably will. In fact, if we model automation as just, you've got output proportional to capital to the lambda instead of to the gamma, and capital accumulates in proportion to output as usual, then you get hyperbolic growth, right? You've got robot production per robot exploding. So that's y over k. It's proportional to k to a positive power, so it's just going off to infinity. You can sort of get around this. So if you say that specialization increases not output but consumption because we love variety, but it doesn't increase like our efficiency at producing capital goods, right? Just consumption goods. Then you've got consumption proportional to k to the gamma here, but capital is just growing exponentially, right? So you've got, robots building robots. While they're building robots, they're just as productive as they ever were. But while they're producing consumption, because there's ever more of them, consumption grows kind of super linearly in the number of bots in the consumption sector because those bots get to specialize and create not just larger quantities of the old stuff, but a kind of finer gradation of varieties that we might like. I'm just going through this to build intuition. Yeah, I don't think anyone really believes that this is how the world works, and specialization is, it would be pretty extreme if it was responsible for all of growth, and it would be even more extreme if it only applied to consumption and not whatsoever to capital goods. But I just and also like if this is all there were to full automation, this would sort of contradict this point that it should be possible in principle to have quickly self-replicating complex systems, capital goods of all kinds. So I'm just kind of going through this to illustrate the general point that like once you introduce a new source of growth, besides R&D, then automating R&D can have not so much impact. Just to trace out the case in the middle, let's say we, this is just summarizing what I said before. If you attribute historical growth to some extent to R&D and to some extent to increases in specialization, this is like increasing returns to scale thing, then output per person is going to grow. This is output per person. So then take the growth rates, is going to grow by the sum of the two things, the growth in technology produced by R&D and the kind of returns to scale point. So if we retain our Jones research function for what's pushing up A, it's just growing at rate lambda over beta GR, then, let's say you observe that research inputs have been growing at 6% a year and that output per person has been growing at 2% a year and population at 1% a year. Well, if you think that gamma is 1, so you just think there's constant returns to scale, no specialization, then you're going to infer what we've been inferring this whole time, which is that, technology has been growing at 2% a year, and that means that lambda over beta is a third. But if you thought that actually we had like these really strong increasing returns to scale and actually gamma's 2, then you're going to attribute, we've got this like 2% growth in output per person. Well, you're going to say that gamma minus 1 here, that is 1 times that 1%, that's giving us 1% of the growth in output per person we've observed. And so only 1% has been driven by this 6% growth in the researcher population. So lambda over beta is only a sixth. And so if you make these kind of adjustments, you might be less likely to conclude that lambda over beta is greater than 1 in the AI context, even if you want to make last lecture's sort of upward adjustments. So that was the specialization example. Briefly, another example is, say, we've been growing historically largely due to decreases in misallocation. So there's this paper from a few years ago estimating that about a third of growth in the US over the last 50 years has been due to decreases in misallocation of talent across jobs, purely via decreases in race and sex discrimination. And of course, those aren't the only kinds of discrimination. So this could be a really big deal. And it's presumably a pond with relatively little to fish out, right? Not that we've like fully solved discrimination in the world today or something, but if we did, we wouldn't increase output by like 100x. Like I feel like we've picked the low-hanging fruit. We have, we've eliminated the most blatant kinds of discrimination, and so we're quickly going to max out the increases in output per person from this source. So let's say we take that 1/3 estimate. That would mean that the lambda over beta relating the growth rate of research inputs to like a sustainable growth rate in technology, it's not a third. It's not that technology grows a third as fast as the research inputs, but actually, historically at least, it's only been growing 2/3 that fast. There's this constraint we hadn't been appreciating, and we'll slam into it once we relieve the constraint that we were thinking of AI as relieving. In this case, the constraint that there's only so many people doing R&D. The other side of the coin is that once you realize that there was this constraint holding you back all along, in some cases you'll think that, well, maybe AI will relieve that constraint even more than it would relieve the original constraint I was thinking about. And so AI could open new sources of non-R&D based growth through better coordination. We'll talk about that at the end here. Better governance, indirect better governance via just like better informing voters about what the consequences of policies would be, so that politicians can get away with less tomfoolery or what. Any thoughts on non-R&D based growth and what that implies for the automation of R&D?
Is there anything that we can say about R&D is alpha responsible for growth? And we have some guess about how we can do that, or we're very much just making it?
I'm not aware of a methodology other than to try to back out other sources of growth, right? Yeah. So I talked about the misallocation thing. Another non-R&D based source of growth that Zach will talk a bit about tomorrow morning is just kind of the sort of natural organic experimentation that goes on when firms change their business practices, and the ones that just happen to be better outcompete the ones that are worse, right? That would be like pure natural selection or something. There are attempts to kind of estimate that, at least in a sense. You can ask to what extent is growth in industry level TFP attributable to new discoveries, new patents and stuff, as opposed to the more productive firms existing at the start of some period outcompeting the others and just growing faster than their competitors. Some of which will just close. And I think ballpark estimates there are maybe a third of industry level growth is due to the sort of natural selection type thing. But you'll have a bit more to say about that.
Yeah, and I was going to say in that Erdo and Barnett paper that I mentioned at the very beginning, they cite these numbers from the BLS that only 20% of labor productivity growth in the U.S. post 1998 has come from R&D, which is based on this BLS data. I think there's reasons to think their methodology might be not capturing the true spillover effects, but they have what? I'll send them to it.
Okay, great, thanks. Just for the recording, basically Zach answered Parker's question that I had danced around and not answered by saying that someone actually has an estimate and the estimate is 0.2, even if we might disagree. Okay. Yeah, just as an aside, I think the thought that AI would lead to really dramatic or really sustained growth purely through better coordination is sometimes seems a bit utopian. The thought sort of well, we already have governments, how much better could we get on that front? Or even like, should we even think that it would help, right? Like maybe AI could facilitate this integration somehow, as we all lock ourselves into our, custom designed LLM echo chambers or something. I think, if you look at the broad sweep of history, it's just the correlation has got to go the other way. Like as we've had more intelligence and more growth and so on, we've been coordinating on ever larger scales on average. So if I had to bet, I would think that, the trend would tend to go in that direction, but obviously that's going to be super speculative. Okay. So a deeper, I think, constraint on growth that you could run into by even after automating R&D is that R&D effort might be imperfectly parallelizable. Now, the Jones model accounts for that by sticking a lambda on top of research inputs, right? A lambda that might be less than 1. But it could be worse than that. So just as a first pass example of how it might be worse, there's some papers out there that sort of kind of have a model that looks like this, where you have an exponential growth rate of technology that increases as research inputs grow, but it's bounded. So even if you had like infinite research inputs, you would still just have some maximum exponential growth rate. This isn't actually, I'm like way oversimplifying, so that this isn't actually the model in those papers, but it's in some respect, it's sort of the same. And so on this story, yeah, we've had like, we reconcile this like Jones's big observation that we've had population growth and even faster, we've had researcher growth, and it's not yielded super exponential technology growth. But that's not because ideas are getting harder to find in this nice sort of exponential way, but just because there's this hard bound to the parallelizability of R&D effort. So R can grow, but GA is still going to be bounded. One way you could think about this is that you need lambda over beta to be finite. You can't have the Romer assumption, which lambda is positive and beta is 0. That would imply ever accelerating growth, given population growth. But you can sort of maintain it with like beta equaling 0 and lambda equaling 0. In a way, you kind of see that? Beta is 0, the exponent on A is 1. But the degree of like diminishing returns to research effort is, it's not like you've got a lambda that's like a half or something. So you've got square root, it goes to that bound, you've just got that hard ceiling. Now at face value, this R&D function would imply at least a little bit of growth in the growth rate as R has grown, which we haven't seen. If anything, we've sort of seen the opposite. And it also raises the question of why we've bothered pouring ever more people into R&D if like it hasn't been paying off, right? So it's kind of a trade-off. either historically the increases in R have been yielding ever faster growth, or it's like we should just have like a fixed number of people doing R&D, and then like everything, you know what I mean? As the population grows on the margin, everyone goes into production because you just hit the ceiling. But I think there is an insight here, and I'll try to spell it out. So again, Jones's functional form is designed to accommodate kind of 3 facts. 1, that ideas seem to be getting harder to find. 2, that it seems like R&D is imperfectly parallelizable. And 3, more specifically, that a constant growth rate of the research inputs, that 6% or whatever, has translated to a constant steady state growth rate of technology. So you can, you can do the trick of like finding the growth rate of the growth rate, setting it equal to 0, and it's, the path of R that maintains a constant GA asymptotically is a constant GR. Because things are all exponential and base to power, it's all constant GR translates to constant GA. But there are many models besides that that meet those conditions, and I think people just haven't really explored the space of them. And there are some issues with this functional form when you think about it. The first and milder issue is that, as I think I mentioned earlier, people have tried to estimate lambda in different domains, at the firm level or whatever, and their estimates are all over the map. Now, it could just be different from circumstance to circumstance, but I just, there's something of a mark against the theory. But the second problem with the theory is that it can't possibly be right when you think about it. Right? It implies that if you just had enough research inputs, A would explode. So if you have an assembly line and you bring in loads of engineers and management scientists and so on to think about how to speed up the rate at which we're cranking out the cars or whatever, if you just stuff enough of them in, the assembly line will be moving twice as fast in 5 minutes. So I think something closer to the right model has to be something kind of like this, where the rate at which you make technological progress rises as you use more research inputs, as you throw in more engineers, so it rises in R, but it only rises toward a ceiling, okay? So this is kind of like the model I was kind of attributing to Lashkari and Aghion et al. Before. But that ceiling itself can rise as the technology advances. So right now, the best technological tools maybe that we have are human engineers or something. So you get a large quantity of them, a lot of R, and you put them in, you set them to work, and how fast they make progress rises in their number, but only toward a ceiling. But if we had nanobots or something that we could send in, and we had a lot of them, they could make progress much faster, right? They could eat up the whole assembly line like termites and build a new one. 5 minutes, maybe. So when A is high, you've got a higher ceiling for how fast you can make progress. That makes sense? And then high R means you have a lot of the capital or labor or whatever, but you've got a lot of the research inputs that are embodying the technology that you have. I'll go through 4 examples of a model of roughly this shape, capturing a phenomenon we see in AI research in particular. And then we'll think through the implications of it. So first, as alluded to before, the big advance of developing a transformer and discovering that it could be run on GPUs was that it allowed us to use more compute simultaneously to train a model. You could train a modern LLM on CPUs, but it would just take ages and ages because you can't use that many of them simultaneously, effectively. The computations then have to be done in sequence, and so the rate at which you're kind of improving a frontier LLM is going to be really slow because each training run takes a decade. So with the given architecture, the speed of training, it doesn't grow unboundedly as you scale up the compute, only up to the point that the architecture permits the work to be parallelized. Oh yeah, there you go, 100x. So training runs now are 3 months, so it would take 300 months. So this is a low A dot, even as R is growing. Okay. With this specific example, Erdel and Schneider-Joseph have a paper showing that as you try using more and more GPUs simultaneously on a training run, they're going to be more spread out and the latency is going to rise, and you're going to be utilizing them less and less. And there's a hard limit, which is that even if you just don't care about the utilization, but you're just willing to use as many as you like, a current roughly standard 3-month length training run can get up to could train a model 100 times bigger than the current frontier model, or at least one as of the end of 2024, but no bigger. Beyond that, even if you're willing to have all this sort of like wasted, semi-utilized, like very high latency, GPU compute in the process, you're going to have to take longer to complete. Does that make sense? So that ceiling's rising as we develop bigger chips. Currently, slowly. I mean, if this constraint started binding more, it might rise faster because like R&D would be redirected based on the kind of same logic we were talking about with Asimov 2003, right? Like we direct our technological efforts toward relieving the main bottleneck. So historically, that's why maybe Uzala's theorems held. We've been developing labor augmenting technology. We'll develop parallelizability augmenting technology like bigger chips with lower latency. If this becomes more of a constraint. But anyway, point is the ceiling exists. You wouldn't see it in a Jones kind of version of the frontier model production function. And indeed, it's already kind of binding in the sense that like training run length has been increasing. So I said it was around 3 months, but like it used to be a bit shorter and it's getting longer all the time. Okay, so we've got this latency wall. If you're going to kind of limit yourself to high utilization, right? So you're not using all these chips on the side in a way that, if you try throwing more chips at the training run, their utilization is falling and falling, and it's falling fast enough that even infinite chips gets you only this much compute. See what I'm saying? But if you restrict yourself to high utilization, you have you have the ceiling. We're kind of approaching the ceiling, and the ceiling hasn't really been rising very fast. I think this graph is inconsistent with something I said here. Yeah, okay. So this is if you're restricting yourself to at least relatively high utilization. And the ultimate latency wall is a bit higher than that. Yeah. Training runs getting longer over time. Do we get that example? Okay. So I think you see something very similar kind of wherever you look. So example 2 will be how quickly you can crank out the inference, right? So for some very, very narrow kinds of R&D at least, how fast it proceeds will just literally be how fast you're able to like produce the information that is, that is the inference. But I mean, this will be especially true in those domains where like we're making up, like we're using loads and loads of inference, right? Like, do we all know like ArcAGI? There's this sort of IQ test for AIs that's designed to be the kinds of questions that people can answer easily, but are hard for LLMs. And there's some questions that people can answer very, very easily that like if you give an LLM, like I don't know, weeks of inference, it can figure out the answer to. Well, that'll be sped up if we can speed up the inference. But you can't speed up the inference just by using more R, just by using more compute at the technology you have at a given time. And this is because the way transformers work, the tokens have to be produced in parallel. And basically, you can parallelize the production of a single token, right? But you can't simultaneously be working on one token and on the next token. Because what you want to say for your word number 2 depends on what word you chose for number 1. Interestingly, this isn't going to be right for so-called diffusion models. It's like the way we typically make images, you sort of, I don't know the details here, but it's something like you start out with a noisy image and then you fill in the details. And it's sort of like you sometimes see painters doing this, like Bob Ross on YouTube or whatever, like use a spray can for like the first version of the image, and then they'll fill in the detail more and more. And there you can have different people working on different parts of the canvas at the same time. That's cool. You can imagine producing, in fact, papers are sometimes written this way, right? You have different people working on different parts of it together, kind of writing outlines in ever more detail until finally it crystallizes into a paper. But not if you're using a transformer. If you're using a transformer, one token has to follow the next. And so and what this ends up meaning is that there's a cap on how much compute you can productively use at a given time to serve. Y'all know what I mean by inference? Sorry, I should have maybe clarified. Like when you ask an LLM a question or whatever, and it produces an answer, that's inference. So it's not the compute that trains it that makes it to begin with. It's when you're running it. Sorry, should have mentioned that. So yeah, so if we were just stuck with CPUs, you couldn't produce 100 tokens even in 2 seconds, even if you tried using 100, or all the CPUs in the world simultaneously. But you can do it with a 2021 NVIDIA A100. And that ceiling, again, I think it just hasn't been rising very fast. We're all familiar with this, right? When you get a new computer and it runs like faster than the old computer, that's because it's kind of got a better processor usually, not because it has lots of different processors side by side. This also kind of interacts with the point we were discussing before, where maybe like the benefit that you get from having a big head, literally or metaphorically, is that there's just such low latency across the different, the different parts of the brain or whatever. So I'm not a neuroscientist either, but just from common sense, it seems like there are some complex sequences of thoughts that like one genius can execute more quickly than arbitrarily many people of average intelligence, however well coordinated. This isn't to say that there are some insights that a genius can have that the rest of us could never have. I'm just saying they get there faster. Right?
But by latency here, meaning like the speed of communication.
Exactly. Yeah, because that's kind of what you need to like orchestrate the whole, it's, yeah. Good. A third example would be model size. So let's say let's say we're not running into this constraint. Okay, so let's say we have our NVIDIA A100, and we're not using all of it at once. So we could sorry, how does this example work? I thought I looked into this very carefully, and I'm realizing that I'm not sure how this point interacts with the point that you can parallelize token. Hold on, this works out somehow. Just give me a second. So well, I don't mean to hold everything up. I'm going to come back to this and post to the Slack. But it turns out that how much compute each token costs grows linearly with the size of a model, size being the number of parameters. So this is that n that Zach threw up before when showing the like scaling laws formula. And we'll talk about it more on Monday. But the point is, you can improve the quality of the tokens by having like a larger model that's sort of using more compute for each token that it puts out. And so that's analogous in some sense, where now the A on the right-hand side is the quality of the model, and that's allowing the higher ceiling for how much compute you can productively use at like per second in creating some kind of valuable output, some valuable answer to a question. When we were talking about something similar earlier, the interpretation was that for AIs, lambda might be higher than it is for humans because we can, they can sort of, have a bunch of compute sort of in the same system, and that can allow for like less diminishing returns than a team of people face that have to spend time talking and spend ever more time talking to each other and coordinating their work. the larger the team gets. As for how to model this, as long as parallelizability remains bounded, you could just actually say lambda always goes to 0 as the inputs scale up enough, okay? Right, when there's a ceiling, lambda is going to 0, right? Like for any lambda that's positive, like square root or something, as you scale up the inputs, output's going to infinity. So you could say, okay, no matter how great the model is, there's still a ceiling on how quickly it's producing something useful as we scale up the inference we give it. But oh, I know what I was saying here. Yeah, so I was just saying, let's say we forget about the fact that inference actually takes time to produce because it's like it's so not a bottleneck, okay? Because like in practice, this is basically how we use these models most of the time anyway. It's not like we're actually like the fact that some answer takes like 30 seconds to produce instead of 3 seconds is kind of irrelevant to the general workflow that it's embedded in. But yeah, they're just kind of it can produce higher quality tokens like the bigger the model is, and you can kind of productively throw more compute at it for inference to get an answer the bigger the model is. So you could run like a smaller model for twice as long, but like that's not going to be as useful. So the kind of amount of use you can get out of it for user compute will grow with the size of the model. Anyway, yeah, so you could say that when the models get better, the ceiling rises by more than the ceiling rises as like humans get more, better at doing research or something. We come up with a better research process. The ceiling rises, and maybe on the AI case, the ceiling rises faster. But still, at any given point, like with any given level of technology you have, there is a ceiling. And scaling up R does not scale up the rate of progress indefinitely. You can model it in other ways too, but this would be a way in which you kind of come to this pessimistic conclusion that actually you don't have this like whole qualitative like rise to the growth rate because of the change in lambda, more of like a level effect kind of thing. And then the final example is the one that really does tie into this scaling law formula. Let's say you only have so much data, so we're going to use all the data we have, and we want to improve model performance by throwing more compute at a training run. So again, this is all a bit putting the cart before the horse. We'll talk about this formula in depth on Monday. But think of loss as something you want less of, intuitively enough. You don't like loss, and performance goes up when loss goes down. Now, as the model gets bigger, you have to use more compute to train. In fact, this is the exact formula. This is how many flops you need as a function of how many data points it's trained on and how many parameters it has. So if you only have so much data in D, you can use loads and loads of compute if you want. You can have R be huge. And you'll be using more compute because you're training a much bigger model on this finite data set, and it's going to infinity. But your loss is not going to 0, or it's not going to the irreducible loss, which is really low. Instead, it's going to D times AD to the negative a half or so. Okay, because you need these two ingredients. They're gross complements. Just like left shoes and right shoes, data and parameters, or with the substitution with R, data and compute are gross complements. So you can't make up for a lack of one with lots of the other. What's technology in this case? Technology, the relevant kind of technology will be sample efficiency. Sample efficiency lets you make do with less data. So it's kind of equivalent to getting more data. You see that? So you can productively make use of each data point better. Um, yeah, the quality of the model you have with which to do your R&D or whatever is constrained by how good your software is on a given frontier. So those are just some 4 motivating examples. Let's take a break now for 10 minutes and till 3:20 or something, 3:21. And then I'll kind of explain what the implications of this are, and we'll hear from Parker about a model of this kind as well. All right. Oh, now it's so okay. So if this is how the world works, what follows for growth or technology growth in any little domain, any link in the chain, the building of better machines of all kinds? Well, if we have a constant growth rate of research inputs that's less than that theta coefficient on the outside, okay, so saying A dot is proportional by theta to some gross complements combination of the tech itself and how many copies of the inputs you have. So if GR is less than theta, then you get a steady state growth rate that here will be equal to the growth rate of the inputs, right? Which is just like in the Jones model. Now, not exactly, because in the Jones model, you have that lambda over beta thing, which we'll introduce later. But just, in the kind of simplest version of the Jones model, where it's like A dot equals R or something, right? Constant GR means constant GA. Yeah. And that's what this model is saying. What this model is doing is it's introducing a cap. Because what happens if you start growing the inputs faster than theta, at a rate that's faster than theta? Then you'll run into the cap. Sorry. First, there's going to be because R and A are both growing exponentially, there's going to be a steady state ratio between the two, and here's how you solve for it. But I don't know why you care about that ratio, so I don't know why. Okay. Let's say you have let's say the inputs are growing at rate theta or faster, then A is only going to grow at rate theta. And you can see this by considering just a sudden surge in inputs, like to infinity, right? Like let's say we suddenly unlock the ability to simulate researchers, and we have functionally infinitely many of them. That rho is negative, right? So R, infinity to a negative number, that's just going to be 0. And A dot will be theta A. The 1 over rho will cancel with the rho on top of the A. You get A growing at rate theta. The bottleneck to tech progress now is not those rival inputs, but the technology itself. In particular, that feature of the technology, of the technological frontier, broadly construed, that we're at, that allows for parallelization. We can only make productive use of so much inputs at once, and so A is bottlenecking that. As an aside, if a model along these lines is right, and if we're going to sort of transition from a world in which like R is more of the bottleneck in some domain, one in which A is more of the bottleneck, then the technology that allows for better parallelization will be much more valuable relatively. And having more copies of the R will be kind of useless. Does that make sense? Because like on the margin, if you're trying to stuff too many engineers into that one assembly line, each engineer is kind of getting very low utilization, right? Like you've all probably felt this on a team that had too many people on it or something, on some project. Yeah, so, I mean, this is not investment advice really, but just conceptually, TSMC, who like make the chips, if we've got like more chips than we can productively use at a given time, because you know they're only so big, and because of that latency issue we keep talking about, we can only kind of use so many of the chips at once. Yeah, you'll NVIDIA, which like comes up with the designs for ever better chips, will their patents will become, or like their infrastructure for generating ever better patents of that kind will get relatively more valuable, and the ability to crank out lots of chips to a given design will become less valuable. Yeah.
What's in the context of the
Yeah, the opposite case would be that we kind of stay with things looking as they do now, more or less, where GR is less than beta.
No,
Which
I'm
means-
asking what would be the case TSMC is more valuable than.
Oh, sorry. I'm not talking about the absolute levels of like value. I'm just talking about like how it would shift relative to today. So I'm just saying like, you know, like if A on the right-hand side is imposing a ceiling, and if we're not at the ceiling yet, then
Yeah.
then R is the kind of limiting factor. It's like left shoes and right shoes, but you know, you've got more left shoes and right shoes, and so what you really want is more chips, and having a better design for a chip is like not that important. Yeah.
Is this an argument for why we should expect research to be increasing over time?
Oh yeah. So this is what I'm saying in this last bullet here. It's totally kind of analogous to the argument I was laying out before for why the R&D share of GDP might be expected to rise over time under the right conditions, right? And the idea there is just like, let's say you've got factories and you've got designs for goods, and we're trying to create more utility. Well, if we are kind of rapidly growing how many factories per goods blueprint we have, we're satiating really quickly in those. But how quickly we're kind of racking up the utils is capped by the fact that there's only so much variety, right? And so we will be willing to sacrifice loads and loads of those countless factories we have making each kind of goods to just get a little bit more variety, pushing up the ceiling. So we can like consume, we can generate utils at a faster rate. Because the ceiling and the utility function, that's right. That's like the rate at which we're cranking out the utils. Great. Okay, so those are the implications in the like very simplest version of this like bounded parallelizability. Let's generalize it in two ways. So first, let's say that you still have this cap, but the steady state growth rate given some GR that's less than the beta cap is not just GA, but it's some multiple of GR. So we'll allow for like the kind of, you know, like the Bloom et al. Say, phenomenon where you need to grow the researchers at 6% a year to get tech growing at 2% a year, or whatever. That's very simple to accommodate. Just put some beta both on the A and divide by beta on the outside of the function. Okay. Why does that have this effect? So just think about it, what's going on in steady state when we're not constrained by A. R is growing at some rate, and the right-hand side, that whole right-hand side, is growing at some other rate. Okay? You know how exponentials work. If A dot is growing at some rate, then GA, that's what GA is. Right? So we want the right-hand side to be, let's say we want the right-hand side, we want A to be growing 1/3 as fast as R. Then you want beta to be 3. So if this whole thing is growing at rate GR, this whole thing with the 1 over rho, I mean, this is CRX, right? So it's growing at rate GR. It to the 1 over beta is growing at GR over beta. And so GA is GR over beta. And because GA is GR over beta, you need the beta on top of the A here, or else A will just like inevitably become a constraint because the A on the inside won't be growing fast enough. So then you put the beta back on the A on the inside. So now we're in steady state. R is growing at some rate. A is growing a third as fast. So A to the beta is growing at the same rate as R. So there's a ceiling. We're rising toward the ceiling, but the ceiling is rising as fast as we're rising toward it. And we're never constrained. But the rate at which the whole thing is growing is a third as fast as the rate at which R is growing. That makes sense. Okay. So we've generalized, we still have the cap. So yeah, sort of kind of constraining singularity or something. Even if we estimate that the beta is, less than 1, say, right? So, if you find a beta of 2 or something, a beta of a half, or 1 over 1.2, which would be like the Davidson and Holden central estimate, you'll find, yeah, we're going to, if we start growing R really fast, then like A will grow even faster. But it can't grow without bound, because like you run into this this theta constraint. If you have infinite R, this just reduces to A dot equals theta A. Make sense? So we're not introducing a like ideas getting harder to find itself getting harder thing where like beta, moves over time, which the two toms built in. We're getting a constraint in a different way. But theta could be arbitrarily high, right? So the growth rate might rise a lot. But you might say, oh, well, okay, but like it probably won't rise indefinitely, but that might be kind of a distinction without a difference. Like, I'll move to 60% growth or something would still be pretty extreme. Okay, but you can also restore explosive growth just by realizing that this whole insight about there being a cap on how fast you can move by scaling up R on any technological frontier is totally compatible with explosive growth. You just need some other parameter outside the whole function, like let's call it lambda. And if that lambda is greater than 1, then you're back to hyperbolic growth again. So here, if GR is less than theta, then we have a steady state growth rate of A, which is lambda over beta GR. Why is that? Well, so R is growing at rate GR. A to the beta is growing at beta times GA. So it's growing at rate lambda GR. Lambda GR is greater than GR. So this whole thing is constrained by R at first. See, because this is like going to 0. And so you've basically got A dot proportional to R to the lambda over beta, if lambda is greater than 1. Note that we can't have lambda less than 1, because this would imply that you couldn't sustain exponential growth with lambda less than 1, because for any given growth rate in the A term, the Why can't you have exponential growth here with lambda less than 1? It's because, let's say you've got R growing at some rate and A is growing at some rate. That's why. Because let's say if R growing at some rate and A growing at some rate. The rate at which the whole right-hand side is growing has to be the rate at which this is growing. But the rate at which this is growing is going to be less than the rate at which this is why. Let's say R was not a constraint at all. This is why. This is simple. Let's say R was no constraint. So you had infinite R, and let's say lambda was less than 1. Then you'd have A dot proportional to A to the lambda, which is sub-exponential. You get that? Okay. But you can have lambda greater than 1. And indeed, maybe that's the better way to model this point that you can get ever greater parallelizability. So instead of having that like MA thing from slide 15, well, sorry, I guess it didn't finish this bullet point, but you can replace it with something that ends up reducing to lambda greater than 1. So you might think that even if we don't have it already, we will once we kind of have automated research, and we're not just like scaling up the number of researchers, but each researcher is sort of increasing the size of its head. What happens if lambda is greater than 1? The ratio of A to the beta, so lambda is greater than 1. This is going to grow faster than that. So R will be the constraint. If we have a huge surge in research inputs, in the extreme, if R goes to infinity, then that equation reduces to A dot proportional to A to the lambda greater than 1. So we're back to the old hyperbolic growth case. But if due to automation, we have R growing in tandem with A, right? So let's say R is, the number of chips, and like A is proportional to how many chips people can make. And so, you got a fixed population and so something like that. So R is proportional to A. Then we're back to getting explosive growth if lambda over beta is greater than 1. Because again, so R is going to be the constraint, not A to the beta. So if R is proportional to A, we can just focus on, we can ignore the A here, because that's not the constraint. That's growing faster. So now we've got A dot proportional to A to the lambda over beta. Does that make sense? We're ignoring the A to the beta row, that first thing, because that's growing faster. So now A dot is proportional to R to the lambda over beta, because the rows cancel. All right. So you're going to get a hyperbola, but it can just be a different hyperbola. Because if lambda over beta is greater than 1, and beta is less than 1, then you're going to have A proportional to A to the lambda, not proportional to A to the lambda over beta. Oh, I'm just taking way too long with this. And all right. The point is, there's going to be this ceiling. So R could explode. There's going to be this ceiling. We could slam into the ceiling and only grow exponentially from there. The ceiling, though, could be growing really fast as well. The ceiling could grow hyperbolically as well, but it could be growing at this lambda rate, which could be less than the lambda over beta rate. See what I mean? So you can ask the question, what if we just didn't have the R constraint? What if we had infinite R, right? If we had infinite R in the Jones model, where you have like A dot proportional to, something R to the lambda. If we suddenly had infinite R, then we would leap up, like A would just suddenly be infinite, right? In this model, if we suddenly had infinite R, then you get A dot proportional to A to a power, because the ceiling is rising hyperbolically, but it's rising at A to the lambda if R goes to infinity. And that hyperbola could just be slower. It could be faster or slower. If that hyperbola is faster than what you would get if you forgot about this constraint, then you're going to be constrained by the lack of R. So you're going to get the old conclusion. But if we're rising toward the ceiling and the ceiling is growing hyperbolically, but it's a slower hyperbola than the R is growing that kind of runs into the ceiling, then you're still going to get hyperbolic growth, but it'll be slower because it'll be at the lambda governed by the A rather than the lambda over beta governed by the rho. And it's going to be hard to extrapolate from current data because we only observe the current relationship between the inputs and the outputs, which will be lambda over beta, not like how fast the ceiling would grow if we suddenly had lots of research inputs. Anyway, you can look at the slides. Sorry for not explaining that super well, but Parker will now share the results of a sort of a model in a similar spirit. And he actually has some data. You?
All right, so as Phil mentioned, this is somewhat of a similar idea to what Phil was talking about. Just thinking about what are the bottlenecks that could happen as you have kind of automated R&D. So the specific thought experiment we're going to be thinking about is what we were talking about in the morning, where we're having just only improvements in software. So we're just having, say, physical inputs, capital, compute, et cetera, held fixed because we're kind of just interested in what's going to happen in the short term. So we just wake up one day and, GPT-7 is now like perfectly substituting for human AI researchers. What happens? So what we were looking at this morning, we just assumed that that production function was Cobb-Douglas. And what we're going to try to do is see if that's a reasonable assumption and how much is that going to matter if those inputs aren't if that production process isn't Cobb-Douglas. So we're going to start with first is just the same Jones law of motion that we were working with, but explicitly writing down just as the CES production function between labor, researcher input, and compute, which is going to be C. And then, yeah, we woke up, we have automated AI researchers now, and how does that go into the equation? Well, Z is just going to be the fraction of compute that you're using in research that you're going to run these simulated researchers for. The other compute you're just using to run experiments like we were talking about earlier today. And so the total number of simulated researchers that you can run is the fraction of compute, Z, times the total amount of compute that you have, C, times A, because we're going to think about A as just being the number of AIs that you can run per unit of compute. Does that make sense? So then we get this extra term at L before, but now we get to add these additional AI researchers to the equation. Now, let's think about the thought experiment where C is fixed. What's going to happen? It's going to really depend on rho, kind of in a similar spirit to a lot of the things we've been talking about this week. If rho is greater than 0, then eventually this term A is getting very, very large. This essentially doesn't matter. And so we have hyperbolic growth if we have this condition about lambda over beta being 1, just like all the similar, just the exact same condition that we were talking about for pretty much all of today. But if rho is less than 0, then you can't get hyperbolic growth. Why not? Well, because even if A is arbitrarily high, you're just getting bottlenecked by your limited amount of experimental compute. You have all these super genius AI researchers, so many of them, but you only have so many GPUs, and most of them are just sitting around doing nothing because they're just waiting for the next experiment to run. So this rho parameter is going to be pretty important. So what Cheryl and I do is try to estimate this rho in pretty much the standard way that economists try to estimate this, which is by observing how firms respond to price changes. So the intuition for this is by starting with a model where we just assume that these AI researchers, AI labs are trying to do some amount of research, but we're going to be totally agnostic about what that is. There's some RT bar, which is just some arbitrary schedule that these labs are trying to follow. But for whatever schedule that is, they're trying to minimize the costs that they face to achieve that schedule. So they're just choosing compute and labor optimally to reach this research input bar in response to prices. So if you just take this minimization problem, take the first order conditions, and then take some logs and rearrange, you're going to get this equation where the ratio of compute to labor is equal to some constant plus 1 over 1 minus rho times the log wages over the rental rate of compute. What's the intuition behind this equation? If W over R is rising, that means that labor is getting relatively more expensive. So intuitively, you would expect people to substitute away from labor because it's getting more expensive and buy more capital. So you would expect this term to rise, which means but the degree to which that is going to rise or not is governed by this coefficient, which is saying how substitutable they are. If, say, they're not substitutable at all, then we would expect rho to be
negative infinity.
negative infinity.
So
Yeah, good
1 over
point.
infinity 0.
Yeah, exactly. Thanks for pointing that out. Yeah, exactly. You expect it to be negative infinity, so you're not responding at all in response to the prices. So we gather data from the major AI labs, OpenAI, Anthropic, DeepMind, on the rental rate of compute, which we're just going to use like how much it costs to rent a GPU, their wages, their number of employees, and the number of GPUs used in research. And if you just estimate that in a naive fashion by just taking this equation and estimating it via OLS, you get that rho is approximately 0.6. So you actually get that they're gross complements already. Thank you, gross substitutes already. And the intuition behind why we're getting this result right now is that compute is getting cheaper over time. Pretty much wages are approximately constant. Maybe they're rising a little bit. This is before like the Meta superintelligence $1 billion offers, so maybe things have changed. I'll have to think about that. But W is roughly constant, but R has kind of been dropping like a rock, right? Because of Moore's law-like things happening with GPUs. Go ahead. So the rental rate of compute is we just take from public sources. That's not too bad. Wages, we are using stitched together sources like DeepMind has their public reports. There's like, levels. That has some guesswork, but it's like reasonably okay. Employee headcount is not too bad as well. There's like a lot of newspaper articles and like this is released on PitchBook. That's where we get the data literally.
Compute used in research is by far the most questionable data. So we proxy it by looking at the compute used in training, and then there's some ratios about how much compute is used in training versus research. That is by far the most fuzzy. So like that's where their data quality is definitely the lowest. Go ahead, Joe.
So, for this specification to work, I guess in the cross-organization production function should be what the companies are maximizing. In reality, they can also be maximizing a business goal in addition to the research optimization that maximizes that business goal. And my point is basically, suppose there were like 5 genius LLM researchers, and they were already bottlenecked by the compute, and then now they're at a different phase of scaling out the business, and everybody they hire is actually for scaling the APIs. So the L you are measuring in your data is not necessarily going into this production function, while it's just a different kind of production function completely captured by this framework.
Yeah, that's totally right. So that's particularly concerning about the employees. If you think the fraction of employees has been changing over time, like, at first they're all doing researchers, but now they're all working on APIs, and that's the primary source of L growth, then you're right, we would be mismeasuring L. So that's a good point.
I guess I'd be more comfortable with OpenAI and like these LLM companies maximizing the lifetime profits, while research is being like, or like this research function being a result of it. Then maybe you can somehow internalize that L going by taking into that account of that, or you can also like see if you can get a share of researchers working in particular, or like share of the employment working particularly on research.
Sure. On the former, I think this like minimization problem is correct, formally stated. Like they're choosing the research schedule according to some, business objectives, right? Maybe they don't care about research, right? Sam Altman just wants to care about products, so like RT is 0 or something, or like some very low number. I have no idea what that schedule is, but I think the business schedule is going to tell you what that research schedule is going to be. But for whatever it is, this minimization problem, I think, is still correct. Now, I do totally agree, though, on the mismeasurement bit on LT, that could be a big problem. Phil?
Yeah, so Tim Hua actually is apparently joining us via Zoom, and one counter argument here is that there's only a limited pool of sufficiently talented researchers, right? Like maybe the marginal benefit minus marginal cost of an additional good researcher is actually really high, but we're at a corner solution because there just aren't enough research. Not sure how this would actually change the math.
Yeah, so this is something I'll talk about in objections later, but like this formulation really does rely on the linear prices in compute and labor. So like if OpenAI decided like I want 10 million researchers like tomorrow, right? They could just like buy that. But maybe that's just like physically impossible, right? There just aren't 10 million people that they could just go out and buy tomorrow. Or there's like adjustment costs. You can't like increase your firm that large, and that's not reflected in the linear prices. I think that's also like a important reason to be concerned. But it's hard to know how far are we away from the linear prices world. I think it's just like a reasonable benchmark place to start, but like thinking about nonlinear pricing is like an important extension. Good.
So, you have like supply responses where more people are willing to work for these companies. What would be the bias direction, and like how it would like contribute to the gross substitution case?
You mean like from an econometric standpoint?
Yeah, like let's say there's an increasing supply of L, so that probably decreases W. Like what's the bias here?
Yeah, so something that I'm not going to talk about, but you can do and we try to do in the paper is you could imagine that there's, it's not actually this, but there's like some hidden productivity terms here. And, if you did this and took the logs, you would have some hidden productivity terms here. And you might be worried that those productivity terms are not orthogonal to the prices. So for example, supply considerations could be in those productivity terms or related to those. And so we do things like we try to instrument wages by local wage prices to try to avoid these sort of endogeneity concerns. Which direction is it going to bias if you don't do it? I mean, I can say the results don't change that much, but like in theory, I'm not sure which way it would bias the results in. Zach,
Sorry,
go for it.
on the point about wages not having risen that much, are you guys capturing the potential effects of like equity packages that have risen a lot in value?
Yeah, so we try to do like present value of the equity. So like it just happened that it rose a lot, but like when they were getting paid, its present value wasn't that high. But the exact like even with respect to wages, equity is even like harder to know what is being allocated and how to value it properly. So yeah, there could definitely be measurement issues there. Go ahead.
Just quick one, so please feel free to tell me if I'm just completely just understanding everything, but like isn't it just impossible for rho to be like positive? Like doesn't that mean that essentially you can literally like substitute between compute and people doing like lab researches or that like yeah, isn't that impossible?
I guess maybe you think that you could just have the, GG5 with like a ton of compute and that just one copy would be enough.
Okay, to get like the gains. So like,
Yeah, like
if you've got a goal of doing this much research, you can either bring in people or bring in compute.
Yeah.
Yeah.
Yeah, or like we know all the experiments, like we don't need any of the researchers, they just go home and like all we just need to do is just like wait for the experiments to run. And they're just gonna like run in the clockwork and then we're gonna implement the ones automatically that seemed good and that's it.
Just like you can see us eventually growth change, right?
Yeah. Right, it's an approximation.
Yeah, but
Could be.
What's the time period for the data?
2014 to 2024.
Yeah, I think the limited variable on changing business structure.
Yeah, with like mismeasurement of L, yeah, that could be a problem. Yeah, we try to do some things where we like say this is the number of researchers, but like it's quite a amount of gap. Yeah, like local tech wages.
I guess these guys are being priced on some, I don't know, very specialized labor market.
Yeah. So
Oh, interesting.
oh yeah, I forgot. We have DC. They're only there for like 2 years though, right? Because they're founded in 2023. So
The way to exploit the fact that they can't move.
Pedro?
I'm confused about like how to think of the fact that in some sense, like if there is whatever sort of shock to prices that makes them choose between compute and labor, in some sense that's like a short-term production function versus like a long run, in the sense that like the lab like committed some types of investments that locks them in to a pattern of substitution between compute and labor.
Yeah.
They thought prices were going to be something, but they could have picked a different one.
Yeah, I guess it's like you're like essentially objecting to the linear prices, right? Like you had to commit to your GPU orders and you committed 5 years ago, and even though the prices way changed, there's no way to like adjust your things right now. Is that roughly the objection?
More
Or one
like
way to think it?
So if I understand correctly, like the way you're doing like a cost minimization that you need to produce.
Yeah,
parts.
yeah.
I guess in the sense like maybe the production function is like,
Changing.
the longer production function also requires some like third inputs that you choose. And like, but when you see the price changing, you're like stuck with the production function that you thought was going to be the optimal one.
Yeah.
If you built your factory in a certain way.
Yeah.
And so it's not like the prices that are not linear, but
Sure. Yeah. Like it's misspecified, the production function is misspecified in some way, and that's having some downstream effects. Yeah, I think that's totally possible. Also like time-wise, or should I just keep going or?
Yeah, why don't you just quickly finish up this and then people can go and if they want to hang around and talk about it.
Okay.
Great. I'll just leave the creative things tomorrow.
Okay, sounds good. Okay, let me just do one more alternative result. So an alternate motivation for the production function is you might think it's not just like standard CS in compute. because what matters for AI research is not like literally number of GPUs, but the number of frontier experiments you can do. Like if GPT-4 just came out, the number of GPT-4 style sized experiments, because 10 GPUs might be a lot if you just invented GPT-1, but if you just invented GPT-5, it's not really worth that much in terms of experiments. And so one way we try to accommodate this is just instead of having CT here, just replace divided by T, which is the latest training, the latest largest training run compute usage. And if you do that, but just keep everything the same, you get rho is approximately negative infinity, so that they're perfect complements. Now, obviously, you shouldn't take like the results like too literally, right? There's like large standard errors, whatever. But that would say like, you're not getting any returns by scaling up the number of laborers without compute scaled up as well. And the intuition for this is just the reverse of the intuition here. Frontier experiments have been getting more expensive over time because the size of the models are getting larger faster than they're getting cheaper. But labs aren't substituting towards human labor. And I have some like objections, but maybe we should I can talk to people about if there's specific things that they have in mind instead of like going over the general objections.
You did with the frontier experiment.
Like this one?
Yeah.
Yeah. This is row.
Oh, sorry.
No problem. So big difference, right? I guess this is related to Pedro's point, kind of, right? Like misspecification of the production function, like could matter a lot potentially. So like, yeah, maybe you should be concerned about that.
You also don't need to instrument for wages, right? It's also instrument for hours.
Yes.
I don't know if you think that.
Yes. So we tried some things like instrumenting like for like GPU releases and stuff like that. You also get pretty similar results, but we decided on the local wages as like the most plausible, but there's a lot of things that you could do. Sorry, go ahead. You want to finish?
Does it get close to zero or like closer to zero or not?
I'll have to check on that because instead of measuring in rho, we do it in epsilon, like sigma instead. So I'm getting confused on converting those, which one is like closer to zero. We'll have to talk about that after. Go ahead.
Yeah. To be sure, in this alternative specification, you're assuming that the signal that you get a new experiment goes like the cost of running a new experiment will grow linearly with the latest frontier model.
Yeah, I think you can put it that way if you want.
Don't you think that perhaps growing like exponentially, but I think like if you grow the latest frontier model is like 10 to 25, perhaps it should just be like 10 to 22 experiment and when to get like a nice signal of whether this was achieved to actually studies or not.
Yeah. The one thing I can say is like if you want to take minor deviations from this, right? You don't want C over T. You want like C over 100 times T. That's not going to change anything. But if you want it to be some multiplicative function, like exponential explicitly, then it's going to change. So yeah, the results are sensitive to how you think frontier experiments appear directly. Go ahead.
The L in both the frontier experiment and the previous classification the same.
Yes. Same amount. Okay, why don't I leave it here since we're a bit over? And like, if anybody's interested in like these additional objections, we can talk about it after.